Out of all the requests we saw in the comments for our AMD full lab tour documentary, the number one was the full-length interview with Jason Christensen. You all wanted access to that, and so we've put it together for today. Parts of this interview are already live in our full-length documentary detailing the thermal lab, the device lab, which is this one, and the BrainUp lab from AMD's Austin campus. You all loved Jason's explanations and hosting and his failure analysis lab at AMD, so today we're running the uncut version of that. For a quick background, Jason is the lab manager for one of AMD's many labs that analyzes CPUs for anything as innocuous as curvature of the die to as extreme as device failure. A lot of his lab's work is dedicated to cutting CPUs back to base components, like you see here, and using various cross-section techniques to reveal the silicon for further analysis by scanning electron microscopes or other tools. With that background provided, let's just jump straight into the full-length interview with Jason. And remember, if you want to see the many other labs that we toured, check out our AMD lab tour documentary for a lot more of this. Before that, this video is brought to you by Thermal Grizzly and the CryoSheet graphene pads. These CryoSheets are molecularly stacked in the Z-axis to encourage vertical direct thermal transfer from the IHS to the cooler. CryoSheet pads are made to be easily applicable for a thermal interface and completely avoid paste dryout because it's not paste. It makes them particularly useful for long service life systems with minimal maintenance. They come in multiple sizes for suitability on the most common laptops and desktop CPUs, and you can learn more at the Thermal Grizzly CryoSheets at the link in the description below. Hey everyone, so we're at the AMD headquarters in Austin, Texas, or one of the many AMD branches around the world anyway. And now we are in the device analysis lab. So I'm joined by Jason, and he's gonna walk us through this crazy lab. It's got some really cool equipment in it. We've looked at a bunch of AMD stuff already that'll be in a couple different videos now. But we're focusing on some tools and test equipment today. And I don't know where you want to start, but the saw looks pretty good to me.
Okay,
So.
we'll start at the saw. So, I mean, this is nothing fancy, but it is a saw that we use for, because we'll get parts in that might still be attached to boards or something like that. And it's easier just to cut the board away. So we can use a saw like this for something like that to do it really quickly.
Getting access to whatever the part is, I guess.
Yeah.
And in general, I mean, so how much of the work do you end up spending in the lab on diagnosing issues versus trying to help the design team or something?
So there's basically two FA labs. There's one here and one in Singapore. And because of our kind of proximity to different teams, the one in Austin, we tend to have more design-related debug. And over there, they tend to have more, say, reliability type debug. Now, we both cross and do each other's work sometimes, so it's not a fixed hard and fast rule. But yeah, for us, it's probably maybe half and half.
Okay, and then you have an oven behind you.
Yeah, this is oven. It's not currently on, so don't freak out.
Right. What are typically the use cases here? Because I mean, obviously, we've seen a number of thermal chambers and ovens at AMD today. This is on the smaller side of those. And a lot of the others we were looking at were like longevity testing or simulation of life, stuff like that.
Yeah.
So what do you do here?
So here it's, we don't use them for that, but we could use it after they do their work. There's a phenomenon called BTI, bias temperature inversion. And when you stress a part at high temperatures and high voltages, and you don't really toggle a lot of activity through it, you can get trap charges and stuff that can cause the part to fail when you try to test it again. But you can redistribute the charge. If you can bake it, you can redistribute the charge and recover. And so we consider those types of fails, they're not real fails, you know, they're induced by our testing.
I see.
So we can use this to kind of recover from that and say it's not a real fail.
Interesting. Okay. How about over here? So some of this I recognize. We have a key-end scanner, but can you walk me through what we're looking at? Yeah,
so this is our laser profiler. When the die are attached to the substrate, when they're assembled, and then all the temperatures cool and everything, there's usually some forces on the package that bow the package, and the die is a little bit flexible, so it will bow with it. So this can measure that profile of that bowing. And so you can see on here, our high point is the white in the center, and it's at, I don't know, close to 70, I guess, micron, and the low points are in the very corners where it's kind of reference 0.
And is this a mobile piece of silicon we're looking at?
This would be, this looks like probably a mobile GPU.
Okay.
And you can actually see the tool, you can see the laser etching on it as it...
Yeah, you can actually read it too.
Yeah.
So how do you end up actually using this sort of beyond, okay, I can see there's whatever, 0 to 70 microns delta here.
So this has come, there's been different times where there's been some testing issues, and they use these thermal heads on the ATE equipment that come down and press. And so sometimes we'll have issues where they're trying to test a certain product and maybe they keep cracking it or something like that. And so they might want to see what it actually looks like, what the actual product looks like. So we use it for stuff like that.
The normal design, if typically it ends up convex like this, in like as a factor of the manufacturing itself, or it's intentional. When you take something like an IHS and you then stick that on top of the silicon in a complete package, does it compress at all, or?
Yeah, it does. I can't tell you how much. I know from the work that we do and the way that we clamp parts, most of our work we have to clamp it in and be able to see the silicon. So from our work, we know that it does kind of help level it out. I mean, and it's probably going to be different if it's got a heat spreader on it than, a bare die like this.
That makes sense. What's next?
So this setup over here is this probe. It's like a little one probe station. We call it TDR. It's time domain reflectance. And what it's used for is to help debug assembly issues.
Okay.
And so here we have.
Oh yeah, this is where in the sort of pre-walkthrough I said let's stop and just start filming, because I actually haven't seen just a substrate with nothing attached to it before.
Yeah, this is
unless I ripped the die off. But
yeah, this is a substrate with nothing attached, and then this is the fully assembled product here.
So what is the value of this one for you in this lab?
I guess I'll have to explain how this works.
Sure. Yeah.
So what we do is we look at a golden curve, basically, from a known good unit, and then we send a signal in on one of these pins or balls here, and then get the reflected signal back from it, and then we look and see if it deviates from that golden curve. That golden curve, I'm saying golden, it's green on here, but that golden curve, if we deviate from it at different points, it tells the analyst that we have a problem in the substrate, or it could be in the die, or even the bump interface between the die and the substrate.
Okay.
And so they can kind of isolate, without doing any kind of destructive analysis. But what this is used for is the one thing we don't know when we send a signal in on a fully populated package. We don't know where the package boundary, what that looks like.
Okay.
So we use a bare die to see what the package boundary looks like, and then we know at what point on this curve is basically the package limit. It'll help narrow it down from package, die, or interface. And so then we know the appropriate people that we need to go next. No, our lab actually has, worldwide, we have these 3 functions. We have the package analysis, and that's, again, the assembly related type issues. We have the fault isolation, which is what we mostly do here in Austin. Fault isolation, we keep the devices electrically viable.
Okay.
We don't destroy them. We may have to thin them, and we'll look at that in a second, but we don't destroy them because we have to run tests on them while we're looking through the silicon, shining lasers or collecting photons or whatever we're doing.
Okay. I don't know if that's actually a thing you do or not at this point. It sounds like it's a thing you do.
Oh, yeah. But it is a thing.
But you can also say things like collecting photons. I'm like, sure, and you're like, I'm actually just joking. We don't do that.
No.
So fault isolation.
So we basically find the XY, and then we'll send it to our physical failure analysis team, our PFA team, and then they do all the cross sections and the real pretty pictures that you see that show the actual defect. We like to say, there's 20 billion transistors on the chip, and we have to find which ones were bad.
What's your next machine?
This is just another scope. We can go over here. There's a hand polishing wheel.
Okay. Yeah. So Vince Kingpin, his name's on like some of the EVGA codes. Yeah. This is what he uses to do IHS lapping when he's overclocking.
It's pretty efficient.
Yeah. But I heard that you had a more maybe precise tool or something.
We have. We'll go kind of in order of technology, I guess.
Okay, sure.
So that was a hand polisher. It's just a wheel that spins, and you have to hold the device on it to polish it. So over here we have these are polishing wheels. They're a little more automated than that guy is. They have a puck on the end, and you can we attach the device to the puck with some wax, and then they'll put some polishing pad down here or a grinding pad, depending on how much they're trying to remove. And then this will come down. The wheel will spin around, and it's putting out a continuous stream of water to keep everything.
Cool.
So that's how we used to do all of our prep. And when I say prep, I guess I should say that for the tools that I can't show you, we have, they go anywhere from low magnification using regular microscope, what we call air gap lenses, to really high magnification using solid immersion lenses. And those lenses actually have to come in contact with the silicon itself. In order to get the right focal point, we have to thin the silicon to a certain thickness to match the sill that we're using. And so that's what these tools are used for generally. A full thickness die is, I don't know, wafers around 700 micron or something like that.
When you're talking about sanding down a die, are you taking it to different depths to try and see at different layers, like through a scope, or?
Not for our use. Our use, it's purely just so that we can image. So we have we have an idea where on the die we need to look, but we need to look at it at a high magnification. We might need to polish from 700 down to 50 micron, and then we can land our sill on it, and then it can focus on the circuitry. So but we were talking about the bowing, right?
Yeah.
So what happens on these tools, the limitation we have is a couple of them. One is if the die is bowed like that and we put it on here and we just try to polish it down, it's going to get thin in the middle and thick on the corners, which might not work for us. It depends on where our area of interest is on the die. The other thing is, back when I started here, it wasn't really a problem, but now we have so many more parts with stiffeners on them, and there's so many package capacitors on them. We used to just remove them. For some of the tests, speed isn't an issue, clean power isn't necessarily an issue. We can just take them all off and remove them. But now, for a lot of stuff, we're pushing for that, 5-6 gigahertz speeds, and
you may start influencing.
We can't take the caps off and stuff. And so the solution for that is we start using these are basically like CNC milling tools. They have bits on the end, and you can do anything from grinding. It's basically covered in diamond things. You can grind to remove a lot of silicon, or you can pull these out. So this has like a polishing pad on the end of it. And so then you can do like a shiny polish. So most of the stuff we need to see through the silicon, so we usually like it really shiny, polished very well. So after we thin it, we still have to polish it nice and shiny. Yeah,
I guess basically you're taking the problem of if you have a curvature on the die and you put it here, you're talking about it's agnostic to whatever's being sanded, it just sands the whole thing at the same pace. So this is point-based, I guess.
Yes, it is. And so here's an example.
Okay.
So they've measured this one, so it takes measures all across.
That's cool.
And so it will follow the contour then of the die.
So are these numbers like microns or something?
Those, I believe, were microns, for that. I will tell you that part didn't work out very well, but it works for our example.
Sure. For configuring this one, how much is it human versus machine to tell it where to sand down how much?
So it's human in that for these two in particular, relative to that one, you have to kind of take the measurements kind of by hand.
Do you use a needle or laser?
They have something. No, it's like a.
Like a depth
it's like
gauge?
Yeah.
Okay.
Yeah, that they use. For this one here, this one can take these measurements directly in.
Okay.
You have to take the part out, measure it, but then it can suck that data in, and then it knows what it's supposed to do.
Right. Cool.
And I have an example over here.
Yeah. Let's check it out.
So I've got two identical units here, except this one, if you look, you can hold it if you want. If you look, that's a full thickness part.
Okay.
And this one's been thinned to 50 micron.
Okay. I can definitely see the difference just by eye, but
yeah, so we have this tool here measures the thickness.
yeah.
So you could stick it in. And so there's the number right there. So 53 micron, just wherever I'm aiming on that die. So it's 450.
450.
So on some of the mobile parts,
down to about 53 or something.
yeah, some of the mobile parts, they grind them from 700 down
Man,
to...
that's a big difference. So when you're sanding down from, what did you say the first, 450 or something, the first one, to 50 microns, what is the composition of all that material?
It's all bulk silicon. So the way that the chips are designed and assembled these days, these are kind of upside down. So they're designed this
flip
way.
chip, I guess?
Yeah.
Okay.
So they're designed this way. All the bulk silicon would be at the bottom, and then they would put the layers of metal and the transistors at the top, and then the bumps, the C4 bumps that attach it, and then they flip it over. So everything that we're looking through is bulk silicon. That's why.
So is there effectively, I guess when you do all this, based on what you're saying earlier, it sounds like the part remains functional even though you've taken off 400 microns of material.
Yeah, it can be a challenge on some of our tools that I wish I could show you, but running tests on silicon that thin and not being able to put any kind of heat sink or anything on it.
That's what I was going to ask. Yeah, so the sort of obvious but maybe a little dumb question to me is if you can easily take away that much and still have it work, what's the purpose of all the material to begin with? And it sounds like maybe it's fragility.
It's support and thermal as well.
Okay.
So, because we can tell when we thin the parts, the temperature, the heat doesn't have as many places to go to escape.
Makes sense, yeah.
And so you end up with more distinct heat spots, basically, that can accumulate and get hot and cause damage.
Sure. Yeah, there's less, I guess,
thermal mass.
Yeah, I was gonna say surface area, superior to just mass, but mass has a place too. So it sounds like you, at this point, maybe just use the more accurate machines, or are you still using the?
It depends on what we need. So sometimes if we only need low magnification, those are pretty quick.
Okay.
And for most of our die, maybe not for the mobile parts, but for most of our like desktop and server parts, the die are high enough that we can just, once we take the lids off, we just polish them to get the indium and stuff off, and sometimes there's a backside metallization on there that we have to get rid of, and then we stop there. So, and then that's usually high enough that it doesn't interfere with the caps.
I just noticed these.
I set those out.
These look amazing. This will be a really good shot. So what's going on here?
So I don't know the entire purpose of that experiment,
crazy.
But they basically drilled through the lid with these tools. You can grind it away.
So what am I looking at? I'm trying to get my orientation.
Okay,
on
that's part of a package.
Sure.
And this was just showing they can also do it from the back side,
right?
From the bump side. On top, you see that it's like a piece of copper for support, and there's a bunch of melted wax kind of holding everything together.
Okay. Yeah. So I guess the wax was added by the team here to just to keep it intact.
Yeah. And these were, I think, just
cool.
experiments to show
just
the capabilities
tech
of the
demo.
tool.
Yeah. Is this a first gen Ryzen part?
No, that's older.
Older?
Yeah, that's probably 8-10 years old.
Oh, are we back into like FX?
Yeah.
Oh, it's well, yeah, okay.
I was trying to remember what package that was.
Yeah. Anyway.
Yeah.
the end result is it looks like there's maybe it's monolithic silicon.
Yes, it is. Yeah,
back then.
definitely.
And so, can you explain these? I'll hand it to you.
Okay.
But sort of the different layers we're seeing, where I can see a little bit of copper. I see, I guess, like the mirror finish on the bottom. Is that just silicon?
Yes. Yeah. So you've got the, of course, the lid here, or the heat spreader, and it is made of copper. You can see the copper in there. And then underneath that, you'll hit the indium that they use as tin material. And then you go below that, and probably if they put indium on it, it probably did have backside metallization, which is a stack up of a few different metal layers.
Okay.
Real thin, but to help with thermal transfer, I think. I know gold is usually the top one.
Yeah, gold is in there a lot. And then you get down to...
And then the silicon is, in the very middle. They polished it shiny. So
that's cool.
So this is our SAM. It's a scanning acoustic microscope.
Okay.
It's basically using sonar. So this tray is filled with water. You can see the water line here. And then you put your part would go in. We have these different holders to hold them in place. They go in and they'll be completely submerged. And then you bring this transducer down to right above the silicon level.
Okay.
And then it'll quickly raster back and forth and produce an image over there. Now what it can do then is if you don't have a lid on your part, you can focus those waves and look at different kind of depths within the chip. So it's another non-destructive way of, say, looking at C4 bumps or we can see if there's any delamination, because sometimes when things go bad, you can have layers in your chip peel apart, and so it's good at finding delamination.
Is there sort of there's a couple non-destructive solutions you've mentioned. Is it just case by case or experience to determine what machine or tool you start with?
Yeah.
It's
the job.
Yeah.
Will basically tell us.
Yeah.
And also the priority of the job. If it's all lines are down, we need to figure this out. We might do it one way. But if we got more time, it's not that high priority. We might use more steps
or something.
Yeah, we might do more steps to make sure we don't miss anything along the way. And not destroy anything. What we have here, and I don't know if you can tell what that is by the indium.
It looks like an Epic or Threadripper type part.
First generation Epic, yeah.
Okay.
Yeah. Instead of taking the lid off, we can look at the indium, what it looks like before we disturb it. So this is an indium scan through the lid.
Okay.
And then you can see, if there's any voids or what size they are. There's a spec for the voids, how many there are and how big they are that there's allowed to be. So
that's cool.
So we just check, if we get a part, especially if it's returned from a customer or a reliability fail or something like that, where we really want to find out the root cause, we might send it to here first, just so we don't miss this, and make sure, it wasn't an indium issue or
before you start digging.
Before we start taking it apart.
Yeah.
And we miss it.
That makes sense. I just noticed we can see through the floor here. Is that just tubes for lines?
So everything in here, everything on this whole floor in this building is it's a raised floor. It's probably, 2 or so feet above. And so all the utilities run underneath. So all of our power, water, gas lines, whatever we need are all under there. And for our lab, they put in these plexiglass ones. So usually where there's valves and stuff, so they can just go over and open it up and turn the valves.
So this, you said, still being set up.
Yeah, that's our 3D. That'll be the 3D X-ray when it's installed.
That'll be exciting to have here, I feel like.
Yeah.
Opens up a lot of possibilities.
Here.
What are these test platforms or whatever these are? Fixtures.
So here, look at one. These are, we call them breakout boards.
Okay.
Basically, all it is a socket, and then every pin wired out.
That's cool.
And then all the power supplies wired out. So like when we're curve tracing on that guy, it's easy to just put the part in here and then connect to the pin you want.
That's super cool. Yeah. Instead of having to screw around with the tiny version of the pins on the CPU, assuming you can even get to them.
Yeah, so we have these built for all of our products.
So are these, do these two particular ones we're holding map to a Products that you know the name of?
Let's see. This is Navi 21.
Oh yeah, Navi 24 over here.
So they have different clamps. This one doesn't have the clamp on it. This one has a clamp. It reminds me of kind of like those delidding tools.
It does look like one, yeah.
With the thing, but this top will
pop out.
It'll pop out if you unscrew it enough. But then this screw kind of clamps it, pulls it all down. And again, you see it's open, so we can see the die.
Yeah, that's super cool. I mean, I don't think all my other questions are going to be about stuff that you can't show. So I think
there's a few placards out in the hall from some of our techniques, including some that are out there that I can't talk about. But I can show these if you want to focus on those.
Yeah, we can do that.
We're going to look at these placards right here.
Very large lines for chilled water.
So this one looks familiar. That's the same laser profile image that was over there. This is actually from the SAM, and I was talking about delamination. How you can see it. That's what that's what it looks like.
So die corner, as it says there.
We have.
So this and just to Sam, I guess reading this, I know what it is now, but that was the one we looked at against the wall.
Yes.
That has
Yeah. And then over here is from our thermal camera. They were running a functional test on it says a quad-core CPU. I've been trying to figure out which one that is. I don't know if that's like Kaveri or Lana or something.
So for thermally mapping it like this, I mean, are they just trying to figure out where are the hot spots, where specifically is it respond or heating up? I guess?
So design actually is a big requester for thermal data for us, especially now with stacked die, stuff like that. It gets very difficult. So they request this all the time, and they just want to see, basically, when we're running certain workloads, where is it getting hottest relative to like our thermal sensors and all that are on the die.
Okay.
So we collect that data for them quite a bit, usually, definitely for every new product pretty much now. But they're a big consumer of that.
Do you know what this is?
Yes. Now this is my wheelhouse. So 16 years I spent in the lab before I became manager, and I worked on this stuff. So what this is a laser-based technique. It's branded LVP. That's a certain vendor, what they call it, laser voltage probing.
Okay.
Kind of a misnomer. We're not actually probing the voltage. Can't tell you what voltage it is, but you can point a laser at a transistor. That's what these stars are indicating, where the laser is pointing. You can point a laser at a transistor while you're running a functional pattern on it. Remember I said we keep them all electrically viable for that reason. And then you get an output. You can see what the data is that's toggling through that transistor. So
when you say point a laser at, I mean, I'm assuming you're basically delidded at this point. And then are you also sanded down on the die? Yeah,
this is a very high magnification technique.
Okay.
If you're at low magnification, your laser spot size, it's going to be huge compared to any transistors.
That makes
sense.
They
still are these days, but we work around that. So you run a test on it while you're aiming the laser at it, and it detects changes they look at the reflected laser power, and they look for differences in amplitude or in phase.
Okay.
And then using that information, they can plot, it looks like this transistor turned on, so the signal goes up.
Okay. Laser stuff, always a great candidate for filming, but something that I still often have trouble wrapping my head around. So, well, thank you for the walkthrough of the part of the lab we're allowed to see. There's more here, but we'll have a couple other videos up showing other parts of AMD's facilities. This, however, is the secret cave lab. It is under AMD. So thank you, Jason, for the walkthrough.
Thank you, Steve.
And we'll see you all next time.